Okay, so we're back with another Solow-Swan model question. So this is macroeconomics, and we're gonna work through this story, and I'll show how the algebra works because I'm not very good at algebra, and maybe some other people are in a similar boat. So I like working through it. Okay. So I'll read the story and then we'll get going. Write down the equilibrium law of motion of the physical capital per capita if all labor income is saved. So ST equals WT/LT, which is what I've written right here. Derive the steady state physical capital per capita. So this is important. We know that it's in steady state, which means this. Physical capital per capita at time t is the same at t plus 1, which is the same at the steady state. So it's not moving. So you can just write k if you'd like. It is most correct, and what you will be not losing marks if you write KSS. SS for steady state, okay? And then we're trying to get to this right here. We're trying to show the effect, but we're getting this answer from this, and I'll show you how we get this as well. So this is the original law of motion right here, and we know ST in this case equals WT/LT, and we know what that means. So you have big K, t plus 1 equals 1 less the depreciation rate. No, that's not divided by anything. So this is what you'll have first, but we want this in per capita terms. So we take 1 plus n out from the other side to make this lowercase, which is the per capita. And this right here is uppercase Y at time t, or your Cobb-Douglas production function, not in per capita units. So we need this to be per capita, so that's all you need to do is small y, and then this is the same thing, except you want it to be small k, because you're taking this out of it, okay? And if this is the case, as a reminder, in this economy, we make it so that L equals N. So your L here disappears, and you're just left with a k 1 less epsilon plus 1 less depreciation kt. This is at time t. Okay, so now we have something that looks like this. So important to note that because kt equals kt plus 1 equals kss, we can now replace all this with kss. And I'm going to do that now, so it doesn't confuse me later. Because in steady state, your physical capital per capita does not change. It is steady. It's in equilibrium, right? It's not going to move. So now we can start to take bits and pieces out of this, okay? So what I'm going to do first is I'm going to move this over to the other side. And then I'm going to factor out KSS, okay? And I'm also going to factor out the KSS on this side. So this is what I've done. Factoring out the KSS on this side has gotten rid of the 1 over here. And moving this to the other side and factoring out the KSS has given us this. These two are obviously going to disappear, and you're left with N plus depreciation times KSS equals, and at this point you might be like, okay, well, let's just get rid of KSS on either side. And I am going to do that. Do not fret. But I'm taking my time here so you can see my steps. Okay? Now drop the KSS. So it's N plus depreciation equals, and then divide everything by epsilon A. You want to make this positive, so this flips. You have epsilon A over N plus depreciation, KSS, epsilon, okay? And then times everything, or I'm gonna put some arrows here, KSS, epsilon, times 1 epsilon equals KSS. So KSS equals, oh, did we just get that right, guys? Oh my gosh. It's my lucky day. I learned how to do algebra. Ah! I wrote a 3 instead of epsilon. Guys, no. Okay? So just as a reminder, this is the steady state physical capital per capita when the law of motion is in equilibrium. Therefore, all labor income is saved. That means ST equals WTLT, and this is true. So your law of motion changes a little bit from ST to WTLT, and you get this answer for physical capital per capita.